Hello, welcome back. So now our next step, which is about checking the minimum and maximum steel as per IS code. So the same process that we have followed in the singly reinforced design in lecture 11, we will follow the same process here also. So as per IS code, minimum steel will be 0.85 times of BD upon FY. So putting all the values. So minimum area of steel as per IS code is 235. So we can say that the area of steel that we have provided in the tension side is 1256 mm square. So you can see this area is clearly more than this value. So we can say that the area of steel is okay when we talk about the minimum steel. Similarly, maximum steel as per IS code is 0.04 times of BD. So putting all the values, we can say that maximum area of steel is 5000 mm square, and which is again more than the area of steel provided. So we have provided 1256 mm square, which is again less than the maximum limit. So our steel provided is more than the minimum limit and less than the maximum limit. So we can say that the tension reinforcement criteria is satisfied. Similarly, for compression reinforcement, so in case of compression reinforcement, we will check only the maximum limit. So AST provided, sorry, यहाँ पे, sorry. So there we will provide ASC. So this is ASC provided actually. So ASC provided will be that we have provided is 1609 mm square. So you can see here, so this is again less than this maximum limit. So the area of steel in compression is again okay. There is no minimum limit for compression reinforcement as per IS code again. So now moving to the next step, which is checking the beam for deflection criteria. So for the deflection criteria, we will use the clause this one and points A, C, D. And for beam to be safe in the deflection criteria, we need to satisfy this equation. So in this, L effective is the effective span, D provided, MF1 and MF2. So first MF1 will be calculated. So MF1 is dependent on the figure 4 and MF2 is dependent on figure 5. So this is actually for the tension reinforcement and this MF2 is for the compression reinforcement. So first we will find out the MF1. So to calculate the MF1, first we will find out the value of Fs. So the same formula we will use here. The same formula is provided in the IS code also. So putting the value, AST required was 1254 and provided is 1256 and Fy value is 415.58. So we get the value of Fs as 240.316. And for that, I will be showing you the figure 4 of IS code, and in that we will see what will be the value of MF1. So this is the figure 4 to calculate the value of MF1. So for MF1, we require Fs value and the percentage of tension reinforcement. So percentage of tension reinforcement we have calculated earlier, which is 1.09%. So 1.09% will be here only. Sorry. So 1.09 will be here, will lie here. And you can see this is the curve of Fs. So you can see Fs curve will be of 240. So this will meet here. And similarly, the value of percentage, if we visualize, we are where it will bisect. So this will bisect here. So corresponding to that, the value of MF will be 1. So this time we can find out MF value as 1. Similarly, to calculate the value of MF2, I am again showing you the second diagram to calculate the value of MF2. So figure 5 will be used for calculating the value of MF2. So MF2 is dependent on percentage of compression reinforcement. So compression reinforcement is 1.4%. So there you can see this is 1%, this is 5%. So 1.4 will be something here. So corresponding to this, so approximately value of MF2 will be 1.3. So we can write MF2 as 1.3. So MF1 is 1 and MF2 as 1.3. So now we will put the values, the same value in the slide. So here from figure 4, MF1 value is 1, and similarly for MF2, percentage of compression reinforcement is 1.4, and with figure 5 we can find out MF2 as 1.3. So now we will put all these value in this equation. So putting all the values, you can see here L effective as 5730, D provided 460, 20 into MF1 into MF2. So this product should be more than this one, and which actually is satisfying. So we can say that beam is safe in the deflection criteria. So now we will move to the step 10, and step 10 is about checking the beam for shear criteria. So now in this case, we will find out the shear force first, and shear force actually occurs at the support, we know that, and bending moment of beam occurs at midspan, but shear force will occur at the support. So we will find out the maximum shear force, which is W into clear span. So we will follow the same process again as in the singly reinforced beam. So W we know 29.375 multiplied by clear span. So we get the maximum shear force as 80.78 kilonewton. So this is the shear force that we have to check if it is resisted by our beam, or we are required to provide extra reinforcement in the form of shear reinforcement. So for that we will find out, we will calculate this force in terms of nominal shear stress, and nominal shear stress is V upon VD. So again, putting all the values, we get the nominal shear stress as 0.702. So this is actually the action of shear force in terms of the stress, which we are calling nominal shear stress. So now we will compare this nominal shear stress with the maximum shear strength of the concrete. So maximum shear strength of the concrete, which we represent by tau C max. So for M25 grade of concrete, the tau C max value can be find out from the IS code using the table 24. So going to IS code table 24, we can find out tau C max as 1.9 Newton per mm square. So you can see here the tau V value is less than 1.9 mm square. So we can say that the dimension of beam, as the value of tau V is less than tau C max, the dimension of the beam is okay from the shear force criteria, which means the size of beam is okay. Or in other words, we can say that beam is safe in diagonal compression. So as I discussed in lecture 11, that shear force is to be resisted by the beam. Now shear force has two component. One is diagonal compression and second is diagonal tension. So diagonal compression criteria can be satisfied by comparing this one. So if tau V is less than tau C max, diagonal compression will be resisted, but we need to check if diagonal tension can also be resisted. So for that we need to find out the tau C value also. So as I written here, now we will check if the beam is capable of resisting another effect of shear, which is the diagonal tension. So beam is safe in diagonal compression, but we need to check whether it is safe for diagonal tension also. So for that we will find out we have to follow the condition, this one. If tau V is less than tau C, then we will say that the beam is safe in diagonal tension also. But By chance, if tau v is greater than tau c value, in that case, we will say that shear reinforcement need to be provided. So we will calculate the value of tau c, then only we will be able to compare the value of tau v with it. So tau c depends on the percentage of steel on the support. So now we will calculate tau c value, which depends on percentage of longitudinal steel at support and the grade of concrete. Now we will assume that we have, we will assume that two bars are bent up. So generally we bent up, we do bend the bar to resist the shear force. So there I am assuming that we are assuming two bars are bent up, which means the tension reinforcement bar at supports are 2. So maximum number of bars in tension reinforcement we have provided 4. So as per condition, minimum bar of minimum tension bar at support should be 2. So if we are providing 4 bars, which means we can bend up 2 bars. For example, by chance, if we had 5 bars, so in that case, we could provide or we could bend up 3 bars. So basically, at least 2 bars should be there at the support. So I am assuming here that 2 bars are bent up. So now we will calculate the percentage of tensile steel at support. So at support, this is how we calculate the percentage of steel. So 2 into area of cross section of 1 bar and whole multiplied by the, divided by the effective area of cross section and whole multiplied by the 100. So the percentage of steel at support is 0.546. So from the IS code, we can find out the tau c value. So referring the table 23. So I am again showing you the IS code and will show you the table. So there you can see this is table 23 for the value of tau c, this one. And on the first column, it is showing the percentage of steel. So our percent of steel at support is 0.546. So you can see here 0.546 will lie between 0.50 and 0.75. So corresponding to 0.50, the value of tau c for M25 grade of concrete is 0.31, and corresponding to value of 0.75, the value of tau c will be 0.36. So our value of tau c will be between 0.31 and 36. So for that, we need to interpolate. So I have done the interpolation on the slide. I will show you that. So this is the interpolation that I have done. And after interpolation, the value of tau c we can find out as 0.35 Newton per mm square. So here you can see the value of tau c is less than tau v, because tau v value was around 0.702 and tau c is 0.35, which means the shear reinforcement, this condition occurs. It means our beam is not safe. It cannot resist the diagonal tension effect. And because of that, we need to provide shear reinforcement as per IS code recommendations. Because we also need to resist diagonal tension effect. So for that, we need to provide shear reinforcement. So we will calculate the shear reinforcement in the next step, in the next part. Thank you.